In this video, I've given you a 4 by 4 matrix A. It's being row reduced to this form here. Here's its reduced row echelon form. And our goal here will be to find a basis for the null space of A and the column space of A. You might pause the video right now to copy down the matrix, and then we'll get going. The first thing to do is to recall that the null space of a matrix is nothing more than the solutions to its homogeneous equation. So here we're looking at the solutions to AX equal to 0. In order to find the solutions, we row reduce. I have 4 variables. It looks like there are 2 columns without pivots in them. That's telling us that our solution set will have 2 free variables in it. Why don't you pause the video now and write down the solutions to the homogeneous equation there, and when you're done, write them down in vector form as well, and I'll do that with you. Okay, so we found that the solution vectors X are linear combinations of these 2 vectors here. I have 2 because there were 2 free variables, x3 and x4. Those vectors are very nice and because of the row reduction here, because of the way that we eliminate variables. This last one had a 1 in the last spot for x3 and then zeros below it, only 1 0 in this case. This vector here gets a 1 in the last spot, but nothing in the last spot for the vector before that. So if I was to form a matrix with these 2 vectors in it, I would see a pivot in each column, and therefore these 2 vectors are linearly independent. What that tells us is the null space of A is the span of those 2 vectors. Everything in the null space is a linear combination of them. But moreover, they're linearly independent, and therefore this set of 2 vectors is a basis for the null space of A. Finally, the dimension of the null space is 2 because there is 2 vectors in my basis. Let's now turn to the column space of A. By definition, it is the span of the 4 vectors that make up the matrix A. So these 4 vectors A1 through A4, I'm just calling the columns of A. If I take their span, by definition, that's the column space. However, as we've discussed, you can express every non-pivot column of A as a linear combination of the pivot columns. It's not too hard to see some relationships. For example, if I look at the row reduced one, it looks like the last vector is twice the first vector, and that relationship should be maintained in the matrix A. If I look at the last vector here, it is twice the first vector here. The important thing for us is that that means that it's the pivot vectors, the pivot columns that matter here. If I just take those first 2 columns are the pivot vectors, so these first 2 columns of A, everything else is a linear combination of them, so the span of those 2 give me the column space of A. And more importantly, those 2 vectors A1 and A2, the first 2 columns of A, there they are linearly independent. Why are they linearly independent? If I was to row reduce those first 2 columns in a matrix, I would get a matrix that has pivots in every column, because they're the pivot columns. So they're linearly independent and therefore a basis. The dimension of the column space is the number of things in a basis for it. That's what we call the rank of the matrix, and therefore the rank of this matrix is 2. We could have observed that earlier because the rank theorem says that the number of columns of the matrix is 4 minus the dimension of the null space has to agree with the rank. So number of columns is 4. 2 of them were non-pivot columns. That means the remaining 2 had to be pivot columns. That determines the rank of the matrix. Finally, we could take a geometric approach here, and we could think about the corresponding linear transformation from R4 to R4. I'm calling that T. T of X is given by matrix multiplication, so T of X is A times X. I can't really draw R4, but I think I can get a reasonable looking picture here to understand what's happening. This transformation T is transforming the domain R4 into the codomain, which is also R4. The null space is the set of vectors whose image is 0 and that lives in the domain. It is a two-dimensional subspace of R4, so I'm going to imagine a two-dimensional plane, the null space, which is spanned by two vectors. These two vectors here will do. And every vector on that red plane, every linear combination of those two vectors, is sent to 0. The column space of my matrix is also two-dimensional, so that's also a two-dimensional subspace of R4. That lives in the codomain. That is the range of my transformation. Those are all the vectors that I get when I multiply x by a, because that gets me linear combinations of the columns of A. So you should imagine a plane sitting over here in R4, and the column space of A is spanned by these two column vectors of A. Observe that my transformation is not onto the codomain. It is not onto, because the column space of A and the four-dimensional codomain do not agree.